Hi everyone, this is the last video for Physics 142. And in this video what I want to do is I want to take everything that we've learned in electromagnetism, which we've sort of summarized in Maxwell's equations here, and I want to try to connect it back to light, which we talked about earlier in the semester as being a wave. So I want to see if we can take Maxwell's equations and actually from them sort of show how we might get light, and especially light as a wave. All right. So you can watch the last video to sort of review Maxwell's equations, but there are going to be a couple of things that are useful for us to think about to actually make this happen. All right. So the first thing I want to think about is that when we think about light, light can propagate through empty space. It can propagate anywhere. And so when we think about empty space or a vacuum, light ought to be able to exist there, right? And so we want to know about what would Maxwell's equations be if we're in a vacuum, if we're in empty space. So I've written down what they'll be right here. And so I just want to go through that. All right, Gauss's law said that electric field is created by charges, right? That this electric flux depends on how much charge you've enclosed. But if you're in a vacuum, if you're in empty space, then the charge enclosed must be zero. All right, so this just becomes that the flux through some surface must always be zero because you don't have any charges, all right, the net flux. Now, you can have electric fields or magnetic fields in empty space. Doesn't really matter where they are. So you can still change a B field and induce an E field. So this law hasn't changed, all right? It's still true that there aren't any magnetic monopoles in empty space, so that's still zero. And if we look at Ampere's law here, what we realize is that, well, if you don't have any charges, there are no charges to move, and so you don't have any currents in empty space. All right, so no currents in empty space, no moving charges, but you still have E fields which can change. And so if you have a changing E field, you can still make a B field. All right, so Maxwell's equations here now simplify down for the case of a vacuum where you don't have any charges. Something that is kind of cool that I can write from this is that I'm going to take these bottom two equations and write the fluxes in terms of fields, right? So this equation here, I'll call this equation number 1. We can write that the integral of E dot dl is minus d dt, okay? And then what is magnetic flux? Well, magnetic flux is the integral of B dot dA, right? That's what flux is. Now, I should note, this is not zero, okay? This is a closed integral, right? This is an integral over a closed surface, like a bag of potato chips or something, right? Some closed surface, all right? This is just an integral over, like say a window or something like that, right? It doesn't have to be a closed surface. It's just flux going through any surface. It's not closed, so it's not necessarily zero, right? You can have lines going through that surface, okay? But we can see this now really directly, right? If you change the B fields, if you change this magnetic flux, you're going to create some E fields. All right. Now, this other equation here, all right, we can write this one down. We can write that the integral of B dot dl is going to be, what do we have here? Integral of B dot dl is going to be mu naught epsilon naught, and then d dt. And what is electric flux? Well, electric flux is the integral of E dot dA, right? That's electric flux. And again, this isn't zero because it's not a closed surface. It's just some random surface, all right? And we see here again now very directly, if you change the E field, take the time derivative of the E field, you get out some sort of B field. All right, so we now have this really neat relationship between B and E and B and E, and they're all tied together in these two equations, and that will be very useful to us in just a second. All right, there's one other thing that we need here, and that is that I want to remind you what we learned earlier in the semester about waves and how waves behave. So early in the semester, we wrote down this constraint equation that we called this wave equation. You may or may not remember this, all right? And what the wave equation said is that if you take if you have some wave, which we describe, remember we described the displacement of a particle in a wave with this variable y, all right? If you take two derivatives of that wave with respect to position, all right, that ends up being the same as taking two derivatives with respect to time, except it's different by this factor that's related to the velocity. And, that's maybe a little bit tricky to think about because that's a partial differential equation in math well beyond this course, all right? But the answer to this constraint equation, or what this constraint equation gives us, is the wave function, which we thought about a lot. And the idea of a wave function just said that, all right, this displacement of a particle, depending on position and time, is going to be a cosine function. Right? If you take two derivatives of something, what's something that when you take two derivatives, you get the same thing back? Well, that's cosine, right? And so specifically, two derivatives of cosine relative to x, all right? That we needed a k times x ends up coming into this, all right? And two derivatives with y ends up being related to this omega t term, all right? Two derivatives with respect to t. So the wave function said, well, it depends on cosine, it depends on kx, and on omega t. All right, and so this was the math we used to describe waves. One other thing that I should note about this math is I should note that the speed that the waves traveled, right? V here, the speed of the waves ended up being related to omega and k, right? So we should remember omega is how much the waves, how fast they wiggle up and down, right? And k, that ended up being 2 pi over the wavelength. And so that's sort of how stretched out the waves are in general, right? In space. And how fast they're going ends up being depending on the relationship between those two, right? So we ended up writing that either as omega over k or lambda times f, all right? So that was how fast the waves move. So this is just to all kind of have this, bring this back to your mind here a little bit. And now with this in mind and with this in mind, I want to see if we can connect the two, all right? I want to see if we can take this and sort of get a wave moving at a sort of very interesting speed out of this, okay? So, all right, how are we going to do that? Well, I want to move my board up a little bit here, all right? Because so we'll get rid of sort of regular Maxwell's equations, and we'll just look at Maxwell's equations in the vacuum here. And what I want to think about to do this is I want to think about an electric field and a magnetic field moving through space together, all right? So here I have some electric field, maybe it's oriented up, okay? And I have some magnetic field and it's oriented sort of coming out in the z direction here. Okay, so E's in the y direction, B's in the z direction, and maybe you created this by having a moving charge, right? Maybe you had a charge and the charge created this E field, right? And then you moved it and that created some B field, right? So maybe you had some moving charges or something. It doesn't really matter, right? We know that charges create E fields and B fields, but now I just want to think about the E fields and B fields, however they got there, going through space, all right? And so they're together and they're going to move in the positive x direction here with some speed. And what I'm interested in is, could we describe in more detail the behavior of the electric field and the B field? Could we describe how they're moving? Could we figure out how fast they're moving? And could we figure out, if they're oscillating or if they're just staying steady or what's going on with the electric field and the B field there? And the answer is, well, actually, yes, because we know that the electric field and the B field together, moving together, have to follow these two equations. They have to obey these two equations. So to see how that works, what I want to do is first I've drawn for you a side view of this situation. Okay, so this is the x-axis and the y-axis, so you can see the electric fields are going up and B is coming out of the page. All right. And what I want to do is I want to actually try to evaluate this first equation here. And to do that, I need to draw some loop. All right. I'm going to draw some loop here. So I'm going to take E.dl. And so this is the loop I've chosen to draw. What I've done here with this black line is I've sort of indicated the front of my moving electric fields. So, I maybe have electric field, and electric field fills in all this space, but at some point I want to chop it off. No more electric field to the front here. All right, so this is just kind of the front of my electric field and B field moving together. All right, sometimes that's referred to as a plane wave. We'll see why just a second. All right, so out here I have no electric field and no B field. All right, but in here I have electric field and B field, and I'm gonna walk this loop. All right. And so let's see if we can evaluate that a little bit. So I need to do E.dl over here, right? And so we'll have E.dl, and you'll notice that dl, the path length that I walk here, all right, I'll call, so let's call this delta y, all right? Or actually, I'm just going to call it dy in case, let's say it's not too big of a path I'm walking here, all right? So over here, E is 0, so that dot product is 0. Here, I'm going perpendicular to the field, right? And so when I take the dot product at 0, so here the dot product is 0, here the dot product is 0. And here, when I walk dl, when I walk along this direction, so for this whole distance y, right? When I walk there, well, now I'm going opposite the field, so that's going to give me minus E dy, right? When I take that dot product, when I take this integral here, right? And it's just minus E dy is just this distance that I've gone right there, right? And, the minus sign comes into effect, they're going the opposite directions. All right, so we know that this has to be equal to minus d dt times the flux through this loop, right? So what is the magnetic flux through this loop? Well, it's going to depend on the amount of B field, B, all right, amount of B field going through the loop. And then it depends on dA, and dA, well, that's going to be sort of this distance y, right? The dA is just this area right here. So that will depend on dy, and, I'll call this dx, is this distance from here to here, all right? So B times the area, well, the area is dy dx. And the area vector, the area vector definitely coming just out of the page here if I walk in a loop like this. And so, you get a cosine that they're pointed the same direction, cosine of 0 there. So that works out. All right, well, now if we look at this equation over here, you should notice that we've got two minus signs that will cancel. And we've got a dy on both sides that will cancel. And so if I sort of divide both sides by dx, or, there's a sense of kind of taking the derivative with respect to x on both sides, what I would get is dE dx equals dB dt. All right? That's, if I just move this dx over here, that is what I get from this equation. And, okay, well, that's interesting. So how the electric field is changing sort of with respect to x ends up being related to how the B field is changing with respect to time. Okay, that's kind of interesting. All right, well, this is one equation, but it doesn't quite get us where I want to go. I also want to think about another view of this situation. I want to think about looking at this situation now from the top. All right, so now we're going to look down from the top, and we've got x versus z here. All right, so this is looking down our way from the top, so now you can see the B fields are kind of going in the positive z, right? And the E fields are going to be coming up towards you, right? So, and now I want to draw another loop and evaluate equation number 2 here. Okay, so let's do that. Let's evaluate equation number 2. So now I'm going to take the integral of b dot dl, and so if I, walk around here, right, again, the dot product out here is going to give me 0, right, because b equals 0 out here. So no dot product out there, no contribution there. Here, my loop is perpendicular to the B field, and so no contribution there. So the only contribution here is coming from this distance I'll call dz, is this distance from here to here. That's where my dl's and my b's are in the same direction, right? So over here, now I'm going to write, if I'm, well, I guess I'll just write down here. All right, so we're taking the integral of b dot dl. Well, that's going to just give me b times dz. In this case, I'm walking the same direction, so it's positive. All right, so that's b times this distance dz that I walked. And, okay, well, what about the other side? All right, the other side has mu naught epsilon naught ddt, and now I need the electric flux going through here. So what's the flux in this region? Well, the flux is going to depend on dx, right? This distance x from here to here, and dz, that's the area and the amount of electric field going through, right? So that's E times dx times dz. That will give me E dot dA, right? That's the area, that's the flux going through this loop right here. Well, now you'll notice that I've got a dz on both sides. Those will cancel out. And if I sort of take the derivative with respect to x, or just divide through by dx, right? So I divide through by dx, then that will give me dB dx equals mu naught epsilon naught dE dt. All right. So well, what are we doing with all of this? All right, now here is sort of a cool step. All right, let's, well, I think I can fit this in within the camera range, right? So is everything, sorry, my camera looks a little unsteady here. I don't know why. Calm down, camera. You can do it. You can do it. Calm. Okay, I apologize if it's oscillating up and down here. Okay, so well, I guess that's, very wave nature, right? So, okay, so I have these two equations. Where am I going with these two equations? Well, let's go ahead and let's take another derivative with respect to x with this top equation. All right, take a derivative with respect to x of this equation. All right, and I'm going to, of the whole equation. Okay, and if I do that, then I'll have two derivatives on E. All right, equals dB dx dt, right? And now what I want to do down here is I want to take a derivative with respect to time of this whole equation. So now I will have, this gives me, right, what does this give me? This gives me dB dx dt is mu naught epsilon naught, and then two derivatives on E with respect to time. Right, there we go. And well, you'll notice this and this are the same. And so what can I do? I can take and I combine these, and I can write that two derivatives with respect to space of E is going to equal mu naught epsilon naught times two derivatives with respect to time of E. And this, my friends, has the exact same form as the wave equation up here, where when you have two derivatives with space and two derivatives with respect to time, the solution to that is a wave, right? The solution to that is a wave. What you end up getting is you would get that E as a function of x and y, E is a function of x and t, right, as a function of position, and time is just going to be whatever the maximum electric field is times cosine of kx minus omega t. It's just going to be a wave just like we had before. And you can actually run these equations the other way. You can take derivative with respect to time here and derivative with respect to x here, and you get the same thing for B fields. All right, you get B of x and t ends up equal B max times cosine kx minus omega t. There's a little bit of a phase offset between those, but we won't worry about that here. And so the point is that what we have derived here are that our electric fields and our magnetic fields are oscillating just like waves. All right, so E fields and B fields together, moving through a vacuum, end up acting like a wave. And, well, what kind of wave, do you ask? All right, what is this wave? Well, there's something really suggestive that we can see here. all right? And the really suggestive thing that I want to see, if I move this up just a little bit more, all right, the really suggestive thing that I want to see is that if we take and we compare the wave equation, the wave equation just disappeared, right? Sorry. If we compare the wave equation and this equation, you'll notice that velocity has to be related to mu naught and epsilon naught, right? Those two things are related to each other. And specifically, we're going to get that 1 over v squared is mu naught times epsilon naught, right? That's sort of the relationship by comparing those two equations. And so what I'd like us to do, just in the last couple seconds here, is, well, let's solve this for v, right? So if you do that, you do v equals 1 over the square root of mu naught epsilon naught, right? And what I'd like you to do, and this is a great exercise to do on your own, all right? It's really quite interesting, is you should look up the value for mu naught, right? 4 pi times 10 to the minus 7, and look up the units there, all right? Look up the value for epsilon naught, right? 10 to the minus 12, right? 8 times 10 to the minus 12, and look up the units there, right? And if you work it through with all of the units and all of the numbers, what you end up getting from this calculation, all right, is you end up getting that v is 3.00 times 10 to the 8 meters per second. And we've seen that before. That is the speed of light, all right? So what we learned from this exercise, what we actually derived, is that electric fields and magnetic fields moving together, that they move at the speed of light as a wave. And what is something that moves at the speed of light as a wave? It is light. So what is light? Light is these moving electric fields and magnetic fields together. And so what we have done is we've taken all that we've learned about electromagnetism, and from it we've been able to produce light. We've been able to produce waves that move at the speed of light and through a vacuum. And so hopefully that kind of ties some things together. And is pretty cool. You do not need to be able to reproduce this derivation. And I mean, derivation, this is not a formal derivation. It's a little bit of a hand-wavy sort of unit-stitch derivation, but hopefully you can see a little bit where these things come from, and you find that interesting and intellectually satisfying. So thank you all very much for a great semester. I'll look forward to doing some exam review with you, but that will wrap it up for course content for Physics 142.